Welcome to this demonstration slash explanation slash tutorial on full wave, fully controlled three-phase rectification. And what I've got here is I've got an Excel spreadsheet that I wrote a few years ago actually, and it covers the full wave rectification with full control. And I've also got half control, which I'll go into a little bit later on. And both spreadsheets here, down the bottom here, between the full control and half control, they're both laid out the same. The first thing is they've got the input variables at the top here, so we can input our alpha value, which is our delay, and then the RMS of the voltage of the waveform. And then over here on the right-hand side is a calculation that will go through and calculate the DC voltage that will be seen here at the output of the controlled rectifier. This waveform up the top here, this is a combination, a series of waveforms, and in it, as you can see, the three phases I've labeled coloured red, yellow, and blue. The line across, the big black line across the top here is the maximum voltage that's seen. I'll go into more detail about all these later on. I'm just explaining the diagrams. And across here is the minimum. The big thick green one will be the output voltage that's seen at the load. And the thin green one is the DC voltage that runs through the middle of that. That's what you would see if you put a DC voltmeter in there. Now, each of these other six down the bottom here are the waveforms that are seen at each of the SCRs that are drawn up here. All of them show the output waveform at the top here, and they're all similar. The first two are for the red phase, the second two are for the yellow phase, the third two are for blue phase, and that phase is highlighted. Each of the other phases is grayed out, but you can still see them quite clearly. And then what it's got here in black is the current flow through that particular SCR. So in this case here, we're looking at device number 1, T1 here, this SCR number 1, and this is be connected to this phase here, which is labeled the red phase. It's the one in the middle. The diagram is slightly out, but this one here, on the red phase here, and we can see that when the red phase is in the forward biased condition, diode number one, SCR number 1, will conduct in the forward condition and provide a current down to our load, and that is the only time that SCR1 will conduct. Similarly over here with the yellow phase, and we're looking at device number 3. Here it is here, the yellow phase coming in at the bottom. Device number 3 will be forward biased in the forward direction, and it will only conduct in the forward direction here for device number 3. If we drop down the bottom here and look at number 6 for the yellow phase, here it is here, this is it here, and we can see that in the reverse direction, that device number 6 only conducts for 120 degrees of the reverse direction. Now, probably now would be a good time just to put some values in here, and it'll go through and do the calculation. So let's say we've got an alpha of 20 degrees. So that's what your waveforms would end up looking like. Okay, everything has been delayed by 20 degrees. If we were to make it, say, 30 degrees, we would get that sort of result. If we were to make it 5 degrees, we would get that sort of result. And you'll notice that the DC voltage out here changes. You'll see it drop in the plotting, and the calculation will change. So if we go back to 0, what we were originally, we see here that the output voltage for a 400 volt line voltage, 230 volt RMS phase voltage, 3-phase system would give us a maximum output voltage of 537.9 volts. And that is calculated from 3 over pi times the maximum line voltage times the cosine times alpha. And the maximum line voltage is the voltage between here and here. Between them, what the maximum would be to the minimum. So it's basically from this point to this point. Now, let's go and have a look at how one of these works. And let's pick on, we'll pick on this one over here, the blue phase. So when the blue phase here, device number 5, this one here, when this device number 5 is forward biased, relative to everything else, it is the most forward biased device. That is when it will start to conduct at this point here. It's at 150 degrees. It's not labeled here, but trust me on this, halfway between 120 and 180 is 150. That is when it will start conducting. And so we get a discontinuity, a transient here. And so at this point here, driving into a resistive load, when this is our voltage driving into a resistive load, we will get a current waveform through that device to there. And at this point here, it is no longer the most forward biased device. This waveform here would be, and this one here would take over. So that's how it works. In the reverse direction, it's the same sort of thing. It is this device here, device number 2, will only conduct, there it is here, device number 2, will only conduct when it is the most forward biased. So it'll conduct for this part of the wave, it'll stop here, it'll stop for 240 degrees, and it'll start again. Each device only conducts for 120 degrees. In the forward direction, 120 degrees, followed by 120 degrees, followed by 120 degrees. In the reverse direction, 120 degrees, followed by 120 degrees, followed by 120 degrees. That is all that we're seeing. Now, when we put an alpha in, and I'll put an alpha of, let's say, 20 degrees, we will see the output voltage over here drop and the DC line drop as well. So the output voltage drops to 505 volts, and we saw that this point here reduced. And so what's happening here, for the blue phase, which is the one we had been looking at, instead of starting to conduct here at this point, when the blue is the most forward biased, it is delayed by, in this case, 20 degrees. So it's delayed from 150 to 170. Only at 170 will we allow it to start turning on. Until then, another device is still conducting. Once this one, we allow it to turn on, then it becomes the forward most biased, then it will start conducting. And we see for the next wave over here, at this particular point in time over here, instead of the other one taking over, we haven't allowed the next one to turn on, so the blue one is still conducting, and it will continue to conduct through to this point over here. And the reverse direction, it's exactly the same. It keeps conducting on the reverse direction. Now, how this results up here in our output waveform is these end up conducting through this point down through here. And if you take this line here is our minimum voltage, which will be appearing over here, and this line here is our maximum voltage, which would be appearing up here. If we make this bottom line effectively our ground, this line down here, and then run a voltmeter between here and here, this black line now becomes our base reference point, and this top black line becomes this green one. And if you could put a ruler up against the screen at any point in time and measure the distance between here and here, you will get this distance here and here, because the voltage between here and here is the voltage between here and here, which is the voltage between here and here. Saying it again, this line effectively becomes your baseline, your, what some people mistakenly call ground. It's our reference line, and then this is the voltage up here. And so that's how the full control works. The half control is very similar. If I go over to my second spreadsheet over here, here it is here, just what you saw pop up then was all the calculations that are going on in the background. I've overlaid the waveforms on the top of it. For those of you who are vaguely interested, if we were to zoom out, this is the sort of thing that my spreadsheet looks like actually. We've got pages and pages of calculations that run down through here that are going through and doing everything. And then I've just got them all, the plots just put up on the top there. So if we pop back down to what we were looking at, there it is there. For the half controlled, in this particular case, the control is on the top ones, the SCRs at the top. If we put a delay in there of 20 degrees, we see the same thing. Over here, we're doing our calculation using a slightly different equation. It's 3 over 2 times pi times the maximum line voltage times 1 plus cos of the alpha. Now, here we've got the same sort of thing. The top device, which is our SCR, is doing the conducting in the forward direction, and it looks just like the previous one. But the bottom devices are not SCRs, they are diodes. Their conduction doesn't change from the initial basic alpha equals 0 one. They will conduct in the reverse direction when they are the most forward biased, but there's no control over them. So as a result, our resultant waveform, this is our top voltage, this is our bottom voltage, and once again, if we take the difference between this point here and this point here, we will get this point to this point. So we put this on the scope and made this our reference point. This is our waveform that we get through the top. And so with alpha equal 5 degrees, we get something that looks like that. We get alpha equals 30 degrees, we end up with something that looks like that, quite heavily distorted. Well, it gets a little bit confusing as to what's happening. So if we just drop that down to say 27 degrees, we'll just shape it back up a little bit like that. And that's how the waveforms are built. And I've found this Excel spreadsheet to be really good for demonstrating what's going on and providing a good visual representation. So what I'll do now is I'll just go through and I'll just punch some numbers into it for you to pause and look at. So here's the half wave with 0. It looks just like a normal uncontrolled rectifier with 5. We can only see a little bit there. We put 10 volt. If we put 10 in, things get a little bit more noticeable. If we put 20 in, things are quite significantly noticeable. And I just realized what's happened. This is actually an earlier version where I actually had a beta in there, so I could control the bottom one differently. That's why it's got the second bit. We better put that back to 0. I actually, as I was saying, I actually had one where I could control the bottom here as SCRs to be controlled independently of the top, and that's what this spreadsheet was based on. So when I mistakenly typed in back there, that's why we had a bit of a distortion. So if we go to 30 degrees, we end up with that. Now if we go back to the full control and we give some options here we are at 0, 10 degrees of delay, 20 degrees, and 30 degrees. So that's how the conduction patterns are laid out, and that's how a good visual demonstration of how a 3-phase fully controlled bridge rectifier based on SCRs works, and how the output waveforms vary. Thank you very much. See you later.